So with that, let me introduce Prateek. So Prateek is a senior principal researcher at Microsoft in India. He's also an adjunct faculty member at IIT Kanpur. So folks who are not from India, where I'm from, IIT Kanpur is pretty much like the best IIT, and IIT itself is like MIT or Harvard. So it's the best school. And Prateek, I had no idea that you actually got your PhD at UT Austin. Who was your advisor?
Inderjeet Dhillon.
Oh, I see. Yeah, so I used to be a faculty member before moving here. So, but on the side. So yeah, I didn't quite realize that. So Prateek has been doing a lot of work as of late, in space. He's actually going to be talking about, I assume, maybe like 3 different ML topics today, generally in that area. And Prateek, I think one thing that students will really benefit from it, in terms of hearing from you, some of the ways that folks at Microsoft Research are actually thinking about TinyML, just a little bit of context. And if you don't have slides on it, not to worry about it, but more like just kind of, if you can kind of set the stage about how, for instance, folks at Microsoft look at the space, that'd be very helpful, give them a practical. With that, Prateek, I'm going to stop sharing, and if you can take over, that'd be awesome.
Thanks so much, Dave. Okay, you can see my screen?
Yeah.
Okay, thanks so much. Yeah, so this is, yeah, thanks a lot for having me here. I looked at the course syllabus, it looks really, really amazing. And yeah, it's great that, we now have a course in this very important topic. I believe that, this topic is really key. And that's why I would like to congratulate Matthew. Like, he very, very nicely captured the excitement that I think a lot of us in this virtual room have. So yeah, so I'm, as Vijay said, I am Prateek Jain. I work at Microsoft Research India. I've been here for almost 11 years now. And for last 4 years, we have been working heavily in this domain of EdgeML or algorithms for tiny machine learning or tiny devices. And here, one perspective that we have is that, like, when I think about how you can have machine learning running on these devices, there are various layers, right? So you need, say, like, once you have a machine learning model, you need to quantize it, make it very small. Then you need to sort of compile it in a manner so that it can sort of talk very nicely with a small runtime. And then that runtime itself is doing a lot of optimization so that it can extract whatever use it can out of these really tiny devices that we are targeting. But here in this whole stack, like, one very, very important part is the algorithms, right? That is the algorithms that are sitting at the top. If they are natively small, like, they are not, like, you are not trying to sort of make a 100-layer neural network run on a Cortex M4 class, I think you should be much better off. So, while there has been a lot of work in, coming up with these very nice platforms, quantization tools, how to compile and deploy things on the device. And here, for example, Pete has been a great inventor in this space. And I saw in this course, like, there are several other very nice sort of platforms that will be talked about in this space. What I would want to focus, and what our focus has been, on the algorithmic aspect, right? That can we come up with the algorithms that are natively small so that they can fit on these tiny devices. And when you think about these algorithms, there are, again, sort of 3 different approaches here. So one approach is that you take an existing architecture and then you somehow compress it, and it has been fairly sort of successful direction. There has been a lot of work on this direction, like deep compression, XNORNet. In fact, XNOR was bought by Apple, I think, for some $200 million. So it's a great sort of direction. Then another sort of direction that has been coming up very recently, and folks at MIT have been, Songhan especially, like, his team has been doing some amazing work in this space, where they are sort of searching for better architectures, which are, again, well suited for the tiny devices on which we want to deploy our model on. But there is another sort of direction in which people are working, which is that can we come up with new architectures, new building blocks that natively give us models which are small, and then you can again apply your search on top of that to make them further smaller. You can again apply some more compression techniques like pruning, etc., to make them even smaller. Then you can apply quantization, and you can use one of these very excellent runtimes to deploy those models. So in this sort of line of work that we have been pursuing, we have been focusing on, can we come up with small blocks of networks that you can combine together, and you can have a very strong end-to-end system, which is very accurate, but still requires very small amount of computation resources. And as part of this line of work, we have come up with this library called EdgeML. All our code is online, available, free, open source. So please try it out. And we also have a bunch of applications and examples. I think visual work, Wikipedic is actually one of the examples, but there are various other things like a gesture pod, which can help make a white cane into an intelligent cane, where so that if you do some gestures with the cane, a mobile phone can detect it, can understand those gestures, and can take some actions based on it. So, but as I said, that our focus is to come up with some building blocks that can be used in your end-to-end neural networks, and so that the neural networks themselves are smaller. As part of this work, we have these two algorithms called Bonsai and Proton, which you can think of as either a replacement for your feed-forward network or layers in your neural network, or you can also think of replacement for classical machine learning methods like gradient-boosted decision tree or support vector machines. Those of you who started looking at machine learning after 2015-16, you might not even know about them, but I'll give a very sort of high-level overview of why these methods are also important. Then in the space of streaming data, or in the space of sensor data, which naturally is in the form of a time series, there we have a bunch of algorithms like FastRNN, EMI-RNN, SHRNN, which can be thought of as recurrent neural networks that are specifically designed for tiny devices and for very sort of fast streaming data. And finally, recently, we've been doing some work where we have come up with a new pooling architecture called RNN pool, which you can use with your standard convolution neural network to make the memory requirement of these convolution networks much smaller. And that means that you can actually have fairly accurate, models like a face detection model or object classification model running on an ARM Cortex-M4 class device. So in this talk, obviously, I will not be able to go over all these. I will mostly focus on Bonsai and Proton because these are like really simple methods. But I definitely encourage you to sort of take a look at all these other methods. They have been published at your NeurIPS and ICMLs, and we have the code available on the repository. And please feel free to ask questions throughout the talk. I am happy to answer them. Only issue is that many times I don't think, yeah, like if there is a question, maybe Kobe will tell me and I'll answer them. Okay, so let's set up the problem that we will sort of focus on today. So suppose we want to focus on a binary classification problem that is given a data point X, which lies in a d-dimensional vector space. I want to predict its label. Label can be, say, either +1 or -1. That is, the data point can either be positive or it can be negative, right? So I can basically write the problem as saying that I want to learn this function f, which maps a vector valued data point X into a binary decision that is +1 or -1, right? So this, like, why do we care for this vector value data? Well, your data can be tabular, which, believe or not, is still a very sort of important regime in a lot of industrial problems. Like if you look at any standard recommendation problem, relevance problem in industry, most of those will have data in the form of some sort of table. And that's why, studying this type of problem is important. Now, I agreed that if you have an image or if you have an audio, then you don't want to sort of just take the image and think of it as a long vector, because that's not going to be a good sort of solution. Your accuracies will suffer very horribly. But even for those data points, we can have a bunch of ways of featureizing them. So deep neural networks is one way of featureizing them, but there are some classical methods to featureize again these type of data points. Like in the case of image, before the deep learning revolution, there were like these very popular SIFT features, Hawk features, which are still like fairly interesting, important features that you can use to featureize your data. Or in the case of audio, you can still use features like MFCC to sort of cast your data point or featureize your data point into a vector valued point, or which you can then apply or hope to learn these classification functions. So any questions so far about the setup? Okay, great. So this will sort of take you back almost 10 years, because as I said, that now most of these, like most of the people are not even talking about these classification methods. But in classification, in this sort of vector valued scenarios, there are sort of three very critical or important set of methods that people have developed over years. One very popular approach is that of kernel methods, like support vector machines or k nearest neighbors with certain kernels. And this was the reason, like this set of method was the reason why there was almost a mini ML revolution in late 90s and early 2000s till almost like 2010. These were the methods that ruled the sort of ML roost, and like they were the talking point at all ML conferences. Now, another very popular and practically very important direction has been that of tree-based methods. That is, you have something like decision trees, gradient boosted decision trees, regression trees. So again, in late 90s and mid 2000s, people came up with a bunch of very interesting techniques here to do this classification and like solve various other supervised learning problems like regression, etc. And then finally, we have these neural networks. Because our data is sort of vector valued and a pre-featurized data point, we will sort of mostly think about these neural networks as multi-layer perceptrons. Again, they have been in sort of, they have been very popular since 1990s. But after 2010, with the advent of, or with like, more popularity of GPUs, etc., these techniques have really, really taken off. But if you again like go in industry, and if you sort of have any relevance problem, etc., any tabular type of problem, again, you will see a lot of people using gradient boosted decision trees or support vector machines. And naturally, there have been a lot of thought on how we can make these methods more efficient. Again, like the like in this again, the topic was very popular in late 2010 and all, and there like the focus was not really these microcontrollers. So they were just thinking about some normal CPU device or maybe a mobile device that can run these methods. So in that space, there was a lot of work, especially around support vector machines. And there, the idea was very simple. So let me first tell you what is a support vector machine function and why you need to make it smaller so that you can fit on like tiny devices. So, any questions? Okay. So support vector machine essentially learns a function f of x, which is given by this very simple formula. For describing this formula, we need to define some notation. In particular, we need to define this very important function called kernel function. So kernel function you can think of as a similarity function. That is, if I give you two vector valued data points xi and xj, then a kernel function essentially computes similarity between them. So for example, you can have this very popular Gaussian kernel, which is also called universal kernel, which is given by e to the power minus gamma times the L2 distance between xi minus xj, like L2 distance square. Again, like these kernel functions and this distance function is actually very powerful. They are called universal because they can model pretty much any decision boundary in the world, right? So why did not they sort of, stay at the top of their game? Why did neural networks almost supplanted them? Well, the issue was that the storage time for this storage as well as inference time for the support vector machine methods was extremely large. That is, you need to store order ND bits to even compute this function. N is the number of points here, and D is the dimensionality, right? N is the number of training points. So like, imagine if you have 100,000 training data points, you have to store all the data points to compute your function. And similarly, inference cost was also order ND. And that was obviously like, extremely difficult to sort of deploy in practice, even on really powerful CPUs. Forget about deploying this on a mobile device or on your microcontrollers. So because of this issue, there was a lot of work on making the support vector machines more efficient. One idea was that, the function is given by alpha I, yi, kxxi, yi is the label, and alpha is the parameter that you learn. Like alpha I is the parameter of the classifier or the decision boundary, and this is what you learn. So can you sort of learn alpha i's so that most of them are 0? So that you don't have to depend on all the endpoints in your training data, but you can depend on maybe very small number of points. And there again, there were a lot of approaches to solving this problem. There were a lot of approaches where you first learn a support vector machine, and then you try to prune out some alphas. That is, you try to prune out some data point, and so that your decision function is now dependent only on a small number of data points, and you'll need to store them, and you'll need to infer with them, right? Then there were some other approaches where rather than learning a function first and then trying to prune them, you try to directly learn a sparse function. And then there were a lot of approaches which were like somewhat more successful, where you try to sort of prune the training data itself a priori. And that is, you try to say that, oh, I have 100,000 points. My support vector machine will require all these 100,000 points in memory. But what if I try to find a small number of prototypes that represent these my training data, and then I compute my function, my decision boundary with respect to only these prototypes. And this was like fairly popular approach in 2000, like 2010, 11, 12, where there are these methods like SNC, BNC that were designed by very popular researchers. But again, they never really got in a situation where these methods were almost on par with your standard support vector machines. They were always 3, 4, 5% worse than standard support vector machine on a variety of data sets. Now, there was another approach which was again very popular, seemed like a great idea when it came out, but it did not really take off. And that idea is that of random Fourier features. That is, like if you look at this sort of function, like what is the issue? The issue is that I have to compute this function k of x comma xi for all the training points, and that's why it's so expensive. So the idea was that, can I approximate this k of x comma xi with some low dimensional representation? That is, can I write it as an inner product of some features of data point x and data point xi, right? And here there was amazing theory which said that if you have a Gaussian kernel, then you can just take W to be a random matrix, and that will work like charm. That is, it will approximate this kernel function up to whatever accuracy you want. And because you are able to approximate this kernel function very well, you will be able to get very good accuracies. But unfortunately, this idea never took off because, remember, you need to initialize this W to be, or have set this W matrix to be random. And while it can approximate this kernel function out to arbitrary accuracy, let's say if you set an accuracy of epsilon, it can approximate it to that epsilon accuracy. But to do that, the number of features it will require will be of the order of 1 by epsilon square, which means that if you want an accuracy of say 10 to the power minus 3, you need 10 to the power 6 features for you to be able to approximate this kernel function, which means that already the cost of storage of your feature is already past the cost of storing the data points themselves. And that's why, while this idea was very, very interesting, very sort of theoretically solid, it never really worked, right? So this was sort of the context in which we started studying these two methods that we have come up with that we call Proton and Bonsai. And Proton in particular is completely in this regime of making the support vector machines smaller so that they can fit on really tiny devices. So and it is very heavily motivated by this idea of learning prototypes from the training set. So let me explain how we went about sort of designing this method. Again, any questions so far on the setup, on the problem, why we are even looking at the problem, or what's the direction that we are taking?
Great. Seems like everyone's following so far.
Great.
So, quick question.
Yeah.
That'd be useful for everyone. Are there specific applications where this sort of method kind of generally works as you dig deeper in? I'm just trying to think of what type of data.
What type of data? Yeah, certainly, right? So as I said, that if you have a tabular data, so let's say you, what you're trying to do is you featureize your user in your recommendation system in some manner, maybe through their age, gender, blah, 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 or through variety of their click data or purchase data. And so you have a feature vector for the user, and now you give me a document or an advertisement or an item to buy. I also featureize that item, and now you need to sort of find out if this item is relevant to this user, right? So for that, as I said, that most of my experience is with Microsoft, but I've seen in general that a lot of times people use a gradient boosted decision tree based ranking system to solve these problems. And they also use support vector machines in sort of various situations. Then another sort of setting that I mentioned was like, if you want reasonably cheap, maybe first level object classification system, there again, using the SIFT or hawk features is very interesting. I think there are some, excuse me, there are some commercial tools out there which does some bit of object classification on I think M0 or M4 class device, and they are not using any deep learning systems there. They are actually using SIFT features, and they have made it like reasonably good. Like they are using SIFT features, they combine it with some random forest, and it works reasonably well. Many times they can be like the first cut things, right? For something like the visual wake word. Any other questions? All right. So let's look at Proton. So while Proton is a sort of, I view it as a one of like, tiny support vector machine method, but it is much better sort of motivated through k-nearest neighbor. K-nearest neighbor is also like a support vector machine method with slightly different objectives. So let me just sort of, briefly recall what is a k-nearest neighbor method. Suppose you have a bunch of training points, maybe you have some apples and oranges, and then I give you a new data point X. Now you have to classify this data point X. So what you can do is you can say that, I will look in a small neighborhood of X. And if I see more oranges around this neighborhood than apples, then I will classify this data point as an orange. Okay? So this is a very sort of fundamental method that has been studied for almost 50 to 60 years now. It can be used for any general supervised learning algorithm. It is very easy to understand, debug. It cannot sort of overfit in some sense because you're not doing any training, or the amount of training you're doing is really minor here. But this method again is like, while it has its uses, there are several situations in which it is used in practice. Still, it is not super widespread. And the reason for it is because its accuracy can be very poor in many situations because you do not know how to compute the distance, right? Like when I say that, I look at the local neighborhood of X, I need to define a distance function according to which I'm looking at the neighborhood. And many times the distance function itself might not be clear. You can say that, I will use maybe the L2 distance between my data points or L1 distance my data points, but that need not be the ideal distance for your particular classification problem or for your particular supervised learning problem. Then on top of that, the model size is really huge for such a method because you have to store entire training data so that you can run k-nearest neighbor on it. And because of that, you also have very large prediction time. So Proton can be thought of as a compressed k-nearest neighbor method where we are designing things so as to overcome precisely these three challenges that I have written. And the interesting thing is that by designing this method, we are actually able to produce models that are able to fit on really small devices. It can provide real-time predictions, and still, like, in a variety of benchmarks that we have tried, it provides very good accuracy, right? So what is the Proton method? So the idea is very simple. Suppose you take all your training points, and first, like, one issue is that these training points can be in very high dimensions. So can we first project these data points in a very low dimensional space while still preserving the label information, right? That is, I want to take my data points, apply a very sparse projection matrix. So the projection time is very small, and also the projection, cost to store that projection matrix is also very small. But when I project my data points, what I want is that my points from one class are very close to each other, points from second class are very close to each other, but there's a big distance between points from two different classes, right? So in some sense, while doing this projection, I'm also learning a distance function between my points, and the distance function is enforcing the label itself. So it is a task specific or a classification specific distance function that I'm trying to learn here while also doing projection so as to save on my memory, right? Now, what I could have done is, I take all these projected data points and I would run k-nearest neighbor on them. But that is also not a good idea because, again, the number of points I might run into tens of thousands or hundreds of thousands. I still cannot store them on tiny devices. So now on top of that, what we do is we say that, we will try to learn some prototypes that represent these training points or these projected training points very well, right? And furthermore, we are going to learn these prototypes from scratch. So it's not like I will take my training data or projected training data and try to select some prototypes from it. We are not going to do that. We are going to learn completely new prototypes from scratch. And we will in fact learn the label vector for these prototypes also. That is, for example, this point B2, while it is very close to say Apple class, but it can also give me little bit of sort of push towards orange class also. So the label vector itself for each prototype is also learned. So now the parameters that we are going to learn is the projection matrix, which should be sparse, the prototypes, which should be a very small number of prototypes, and the label vector for each prototype, right? And for this, we can now write down a very simple optimization problem. That is, what we want is we are sort of defining this k nearest a, or a sort of loose form or a smooth function, smooth version of k nearest neighbor prediction. That is, we take data point x, we project it into this low dimensional space using z. Then I find out prototypes which are closest to it. I will give most of the weightage to them. Like this ex function is going to do that. And then I will sort of say that for that prototype, I will predict whatever is the label. I will just sort of add all the labels, and whatever label comes out as majority, I will predict that, right? So it's a sort of smoother version of k nearest neighbor. And if you look at this expression also looks very similar to a support vector machine with a Gaussian kernel, right? So we define our prediction function to be this. I say that I will try to minimize my loss over my training data. And on top of that, we are going to impose this hard constraint that because let's say I know that my memory constraint is so and so. Let's say I have to produce a model which fits in 8 kilobytes of RAM. So I will impose that condition very explicitly. I will say that my label vector, my projection matrix, as well as prototypes, they should not have more than say this KW, KZ, and KB non-zeros, so that I can now store these things in a sparse format, and my model can fit on a really, really small device. And I can also sort of infer with this model in a very efficient manner on this small device, right? So now this problem can be, like this problem seems a horribly hard non-convex optimization problem. Yeah, go ahead. Yeah.
I'm sorry, somehow I missed, like, how do you enforce the memory constraint again? I understand what you're saying with the memory constraint, but how do you
yeah, sorry, so I should have introduced this notation. So when you look at the Z L0 norm, what it essentially says is that the number of non-zeros in Z is bounded by KZ, right? So if the number of non-zeros in a matrix is bounded, then I know that like, the number of parameters to express that matrix is going to be very small, right?
Okay.
So that's the standard trick that we use.
Okay, gotcha. Thank you.
Any other questions about this formulation? Yeah, so what we, so as I said that here we are now going to learn the projection matrix Z, the prototypes and the labels all from scratch with this very explicit memory constraint. And this seems like a very horrible non-convex optimization problem because the objective function is horribly non-convex, and on top of that we are adding these L0 constraints, which are also very, very sort of challenging non-convex constraints. They are not even smooth, but still, like, we still go ahead with this optimization, and we use this very simple trick of iterative hard thresholding. What it does is it tries to do a gradient descent over the objective function, and then every once in a while we'll project all our parameters onto the set of sparse vectors, and that can be done in a hard thresholding manner. That is, I look at my parameter. So if let's say I'm updating Z, I look at my parameter matrix Z. I look at only the top KZ elements in terms of magnitude. I keep them, and I zero out everything else, right? So this is like a very simple iterative hard thresholding technique that we use. You have to sort of combine it properly so that it converges and it works out, but it can be done. And that what it leads to is a very sort of nice system where now I have this Z which is super sparse, I have these BIs which are super sparse, as well as I have these WIs which are super sparse. And what we do is basically run it through the system to get the prediction for a new point. That is, given a new point X, first I will do sparse projection using this matrix Z that we learn. Then we will compute distance of Zx from every prototype that I have. Again, because the number of prototypes that I have is very small, I can do this distance computation easily. I can take top few of these prototypes, like the according to distance or according to similarity, and I will add their labels, and I will just predict that as my output. Right. So again, prediction function is extremely simple, provided that the sparsity in projection is very high and the number of prototypes is very small. Right. Now, as I said that, like, solving this optimization problem seems nightmarish. You do it, you never know whether it will work or not, which is what deep learning is all about. But I come from a little bit of old school of trying to sort of show that the method that we have works out, and especially like in this non-convex regimes. So what we were able to show is that at least in some very simple settings, where let's say if the data that you have, like let's say it comes from two classes, and those two classes are very well separated. And if you initialize your prototypes also well enough, that is, you initialize your prototypes far enough from each other, then what we show is that this iterative hard thresholding method that we describe actually converges to the global optima. So it's not just getting converging or getting stuck in a very poor local optima or a saddle point. It is actually converging to the global optima, provided the data satisfies these assumptions. And even if your data is very high dimensional, you have to learn very sparse Z, still everything works out. And a lot of that works out because of some of the theory that we have developed in this line of work that we call non-convex optimization for machine learning. Sorry for giving this very shameless ad in this TinyML course, but if you are more interested in these non-convex optimization methods, especially these sparsity inducing methods or low rank inducing methods, then please take a look at this book. The reason I'm bringing it up is because when you want to design these methods for TinyML, most of the time your allies to make your model size small, other than like domain knowledge, is sparsity, low rank, and some similar structures like Kronecker product rank, etc. And if you are using those techniques, then some of the methods in this monograph that we have can be quite interesting. Okay, so I think so how am I doing on time? Like how much time do I have to talk about Bonsai?
You're doing pretty well. I think we have another about 30 minutes left in the class, but maybe save some of that time for questions.
Okay, so should I take about 20 minutes?
Yeah, it should be great.
Yeah, so let's go with the next method. By the way, like we have a bunch of benchmarking numbers for Proton, and that also sort of describes how at least we view how we should present numbers in this regime. What are the key things to track? So I will talk about those numbers after giving a high-level overview of Bonsai. So Bonsai is is a little bit different than Proton. Proton was the goal was to have a tiny support vector machine or a tiny KNN method. In Bonsai, our goal was to come up with a compressed tree method. As I said that for tabular data in industry, still people use either support vector machines or they use trees. In fact, trees are more popular in general. So Bonsai, I believe, really powerful method which still can work with very small amount of parameters, small amount of RAM, and small amount of compute. So what is the idea behind Bonsai? So let's say you are given this data set, right, where you have a bunch of positives and negatives. Say red points are positives and blue points are negatives. So if you think about a gradient boosted decision tree, what it does is it applies bunch of axis aligned cuts. So either it will apply a cut along the x-axis or y-axis, right, like these two axes, and it will try to separate out positives from negatives, right? And that's why it will keep on applying these cuts to separate out data points in various sort of portions of this space. And because if you apply too many of these cuts, then you might start to overfit. And that's why in gradient boosted decision tree, you need to have multiple trees. So when you have these multiple trees or essentially a forest, then your decision boundaries become much more smooth and you become much more robust against small overfitting issues, right? Now, one can say that rather than putting these axis aligned cuts, can I have more oblique cuts because they might be more efficient? And yes, you can do that. So what you can do is, yeah, I will take these oblique cuts, put them around my data and try to learn with that. Again, that's a good idea. But still, if your data is very non-linear, you might need to use a lot of these oblique cuts to capture the data, to do this classification accurately, which means that the height of the tree will be very large. And that's again a very real problem that a lot of people had observed earlier, right? so the key insight in Bonsai is that rather than making these cuts to be oblique, we will try to make these cuts also non-linear, right? And that then gives this power to us to make these trees very small, very compact, and still able to capture a lot of very challenging non-linear decision boundaries, right? So for example, Bonsai, what it does is at each node, the prediction is not only say whether I have some theta and theta transpose x is greater than equal to 0. What you're doing is you are now taking the theta transpose x or say v transpose x, you apply 10 hyperbolic on that, and on top of that you multiply some more linear function with it, and this sort of function then is able to give you fairly interesting nonlinear boundaries. It is able to give you very interesting nonlinear cuts, and because it is a tree, you can have various decisions here, right? That is, I will say at the root node, maybe I have this central cut which says that I am dividing my space into two portions. Then when if there's a point which lies below this center curve, then I will go to the left node. And in the left node, then I will again apply this decision boundary. If my point is above this decision boundary, then maybe I'll call it a negative. And if my point is below this decision boundary, then I will call it a positive, right? So as I said, that the main point is because you have these non-linear things that are able to capture various boundaries that happen in real world, we are able to do this with very small tree. Right? Any questions about the basic Bonsai setup and the idea behind it? Okay, great. So based on this, now you can define the Bonsai method formally, and this need not be a binary classification method. You can actually apply to multi-class. You can even apply to regression problem, etc. So how do we do it? Well, we design this method where first we take the input data. Similar to Proton, we again project this data into a very low dimensional space using a sparse projection matrix, right? So we will have to learn the sparse projection matrix. Now, when we are working this very low dimensional data point, we pass it through the root node. Root node has a parameter theta1. It also has parameters w1 and v1. So if theta1 dot x hat is greater than 0, then you go to the left node. Otherwise, you go to the right node, right? And similarly, if your theta2 dot x hat is greater than 0, then you go to the left node, then you go to the right node. And similarly, you reach some leaf node. And based on your leaf node, you have your final decision boundary. You have your final prediction. And in this final prediction is where we are using the non-linearity that we discussed. That is, the final prediction is taken along the path. It says that my final prediction is dependent on the root node and how much separation I had, which is given by 10 hyperbolic of v1 dot x hat times w1 dot x hat. We will also add the decision that I got at my intermediate node here. And I will also add the decision that I get at the leaf node. Great. Yeah. So you said that now we have defined our final decision boundary or decision function, which is dependent on the projection matrix and on these parameters that are sitting in each of the node, right? And this is where Bonsai, I think, differs very significantly from most of the decision trees that, at least at that time, were out there in literature, which is that most of the methods just they use these intermediate nodes or the for navigating in the space, and the final decision was just given by the root by the leaf in which you land, right? And that's where this issue of oblique cuts and overfitting to them will come in. But if you are sort of saying that no, I will predict on my leaf node, but I will also sort of take care of how I ended up at that leaf node. And I will be using fairly powerful nonlinear functions in describing that the decision boundary. That is what gives the Bonsai its power, and that's why it is able to learn fairly small, sparse model that works fairly well in a lot of situations. Right. So now let's see how we are going to learn these parameters in Bonsai. So, so as I just talked about, basically we form this optimization problem where we are learning all the parameters of tree. We just represent all of them as this big theta, as well as this sparse projection matrix Z. So we have defined our prediction function y hat using this. So you will take y hat, we'll take the loss function between y hat and y, which is parameterized by theta and z. We add some bunch of regularization here, and we will also sort of impose this explicit memory constraint. We will say that the number of non-zeros in my projection matrix, as well as parameters of tree, should be less than, say, some b as well as s, and that you can now sort of jointly optimize, right? So again, this is a challenging non-convex optimization problem. In fact, this is a more difficult problem than Proton, because in Proton, at least the prediction function that I had was smooth, right? But in Bonsai, the prediction function itself is not smooth, because if I have theta dot x, slightly greater than 0, I will go to the left node. If it is slightly less than 0, then I will go to the right node. So the decision function can change completely by flipping maybe some small number, like some insignificant bits, right? So it becomes much more challenging to optimize, but we have some tricks to optimize it. So for example, we do not actually train right away with such a harsh decision function. Initially, we train with a decision function which is much more smooth. That is, when we look at theta1.x, we can go to left node with some probability, right node with some probability. So, and we are going to, actually in training, we are going to take both the paths to train all our parameters. And then what we do is, as the training proceeds, we make that decision function more and more harsh, so that it actually exactly resembles this, excuse me, this sign function. That is, I will go to left node when theta dot x is positive, and to the right node when theta dot x is negative. Right? So yeah, bunch of, again, optimization tricks later. We will be able to optimize this model fairly well with this explicit budget constraint, and it gives fairly sort of impressive results, right? So again, like, if you want to do some theory with this, you can, as long as your data satisfies some assumptions. You will have to make some more assumptions. You will be able to show that this simple technique of, like, iteration and doing hard thresholding converges to the global optima. Okay, so let's look at how Bonsai and Proton does against standard uncompressed methods as well as standard compressed methods, right? And again, some of these numbers are a bit old because this paper was published in 2017. So there might be some newer methods which have done a bit better than them, but I think the over point remains the same. All right, so we tried out these methods on a bunch of data sets from a very different set of domains. We looked at some data sets from activity recognition, some data sets from very simple digit classification or character classification problems, some data set from IoT world, like where, let's say, I think there was one data set where microphones were capturing the sound of whales, and based on that, you had to do classification. So we took, like, variety of these data sets. And first, we try to see how does our method like Bonsai and Proton compare with standard uncompressed methods. So I'm not worried at all about how much space these methods are taking. We want to just see, in terms of accuracy, are they, like, meeting the bar? Are they at least in the ballpark of these standard methods? Because if that's not happening, then maybe people will not even look at these methods. They will not take these methods, right? So from that point of view, like, luckily, situation has been, like, on these benchmarks, it looked very good. That is, we compared Bonsai, which is in red bar, and Proton, which is in blue bar, against methods like gradient boosted decision tree, k-nearest neighbor, support vector machine with RBF kernel, and multiple layer perceptrons, right? And what we observe is that in terms of accuracy, at least on these set of benchmarks, like on these 10, 12 benchmarks that we considered, Bonsai and Proton perform very similar, or in fact, sometimes even better than your gradient boosted decision tree and neural networks, etc. Right? But when you look at the model size, our methods are constrained to be less than 16 kilobytes in all these experiments, right? Whereas your support vector machines or neural networks or gradient boosted decision trees can take as much as 100 megabyte or so, while achieving almost the same accuracy. So you can get, like, great 1,000 to 100,000x compression by using these methods, right? Now, when we want to compare these methods against other methods that tries to do compression, the way we report results is based on this model size versus accuracy graph, right? And in this case, model size is a very good proxy for the RAM that you will need, as well as for the compute that you need. So, like, like this is a very special case. In general, I believe that whenever you are reporting numbers in this TinyML regime, like, you have like different methods have different strengths. Some methods might look very small, but their amount of compute is very large, or their amount of RAM requirement is very large. So those should be important parameters. But in this special regime of vector features and these type of methods, fortunately, this is not an issue. So that's why I will just report numbers in terms of model size or the number of parameters in the model versus accuracy, right? And we compared against, like at that time, like whatever was available, we compared against all those methods. So methods like tree pruning, which or this decision jungle, which was, I think, a best paper at CVPR 2015 or so. Neural network pruning, I think this method by Song Khan. I think it was also one of ICLR best papers. SNC method, LDKL, like, so we tried against a bunch of these methods. And what we observed is that in a very low memory regime, like when you want to look at 16 kilobytes or so, only Bonsai and Proton had some reasonable accuracy. Most of the other methods did not even, like, come in 10-15% limit of these methods. And we observed a very sort of similar trend on a bunch of these methods, right? We also did a bunch of experiments where we tried to deploy these models on very small devices like Arduino Uno, which has, I think, an 8 mega processor. We also deployed them on M0 plus class device. And again, like, these methods were able to fit in very nicely on those devices. We could do some more quantization. Like at that time, we did not use any of the standard method or like any of the standard framework there. We just hand coded that quantization, had C++ code or C code running bare metal on these Arduino Uno and M0 plus class devices. And it was doing very well. And in particular, as I said, that, like, we used precisely this technology, like this Proton method, to enable this intelligent cane. That is, we had this white cane on which we had a very simple gesture pod or a very simple device that was attached to this cane. It could be attached to any white cane. You can remove it, attach it. And that gesture pod, all it does is have an IMU sensor, right, to record how the cane is moving in three axis and how it is rotating. And we had a M0 plus class device, which was running on a very tiny battery. And the main point was that this device now was just, I think, about 50 grams. And it, like, if you produce at mass, I think you could have produced this within $5 to $10, right? Now, what it device could do is, like, if you do some gestures like a twirl of the cane or a double tap with the cane or some sort of swipe with the cane or making some numbers with the cane, the Proton algorithm that is running on the device was able to recognize these gestures, because these gestures were in some sense signaled in the IMU data that we were getting. So we took that IMU data, we featureized it in some particular manner. We ran it through Proton pipeline. Proton model was just about 16 kilobytes, so we could fit in very easily on this tiny device. And we could sort of do fairly accurate prediction locally without sending data to Bluetooth, from Bluetooth to the mobile phone, right? Which meant that the device lasted about 14 to 15 hours in one go. If we would have sent all the data to mobile phone for detection, then the device battery would have lasted only about 1 hour, because Bluetooth consumes a lot of power, at least on these M0 plus class devices. So that sort of was a very sort of interesting exercise that we have. And on this EdgeML repository that we have, we actually have all the data, the design spec, the 3D printing sort of sheet, everything available. So in case you are interested in gesture pod, like exploring it more, like, please go over it. And if you have some questions, definitely let me know. So I guess I should stop. Have some more things. Yeah.
So one of the questions that came up even in the discussions when students read the Bonsai paper was, why is it that as the model size increases, the accuracy drops?
In these situations, or here, yeah. So so many times what happens is that, like, this is sort of a little bit of a game between regularization and model representation power, right? That is, when you have smaller model, then in some sense the sparsity itself is regularizing the model. So for certain problems, smaller model is helpful because you are regularizing it better. But in certain situations, maybe you want more representation power, and that's why by increasing the model size, you have more accuracy. And on top of that, like as I said, that we are solving this non-convex optimization problem with crazy hard constraints. So many times you can also lay the blame on the footstep of the optimization method, that maybe the optimization method was not able to get into a very good region or very good zone.
Okay.
Any other questions? Like how much time do we have? Because I had some more material. If I want, I can go over it.
Yeah, you can. So we have until 45. But I think, you know, if anyone has any questions, just feel free to jump in now, but you can continue.
Yeah, so maybe we can take questions right now, and then I'll just give a very high-level overview of another sort of interesting line of work. We have seen sort of, you know, very useful in a lot of settings. No questions? Okay, great. So let me now give you a very high-level overview of this work that we call FastRNN, which is essentially a new RNN block similar to LSTMs and GRUs, but it is natively much smaller than your LSTMs and GRUs. And that's why it is very applicable in a lot of IoT devices settings. So, so RNNs are very, like I believe that RNNs are very important for IoT world. And the reason for that is because RNNs are natively very small, right? Like their model size in general is very small. The amount of memory that they need is very small. The compute can be a bit higher, but again, on these tiny devices, you do not have any parallelization. Like most of them do not have much of a parallelization. So even if you are using RNNs and it is going over the data sequentially, it does not sort of, you know, hurt you too much compared to say running a much more parallel CNN or a transformer, right? But because its model size is small, it has lower working RAM requirement, and because it is very well applied to time series data, I at least believe that, you know, it's a very sort of important tool in this domain. So again, why is time series data so important for IoT devices? Well, IoT data, like IoT devices naturally produces time series, right? Like they are sensory data that observe the environment at regular intervals. So for example, if you have a microphone, it regularly observes the environment, records whatever vibrations are there, and it produces this audio signal. And similarly, if you have, say, like, you know, soil moisture sort of device, or it will, like every few minutes or every few seconds, it will observe what is the moisture level, and based on how the time series is going, you would want to maybe turn on your sprinkler or turn off your sprinkler, right? So a variety of these applications come in this domain of, like, you know, understanding this time series data and taking some action based on it. And as I said, that I believe that RNNs are very well suited for it, and in a variety of settings we have seen them to be very useful. So so what are recurrent neural networks? Like, why are they very useful in this time series domain? So the idea is extremely simple. Recurrent neural networks are state-based neural networks. They maintain a state, right? So let's say at the tth step, you observe some data point xt in your time series. These neural networks, because they have some state, let's say ht, they will take this input xt and current state ht, and it will modify the state of the neural network to ht plus 1, right? So you keep on sort of, you know, modifying your state as you see these data points, and in the at the end of this time series, you will get some final state, which can be thought of as a featureization or summarization of all the data that you've seen so far, right? And then based on this data point, you want to sort of apply some classification, and you can, like, you know, your classification can give you, can tell you that, oh, in this audio was there a segment which called out hey Cortana, or should I turn on my sprinkler, right? And note that, like, you know, this final feature vector or state that you get can be thought of as feature. So you have pre-computed feature. On top of this pre-computed feature, you can apply Proton, Bonsai, and they will work perfectly fine. So the main goal here is to understand how we can generate these states or these features, right? So your vanilla recurrent neural networks are fairly powerful. They model your states ht plus 1 as some sort of nonlinear function of affine transformation of xt and ht. So you have some matrices w and u that does a affine transformation of your current input, that is your current data point xt, and your current state ht. And this is how you keep on sort of evolving your state. So this is like, again, a very powerful thing that can capture a bunch of functions, but these recurrent neural networks are not used in practice at all. I don't think you would have, any one of you would have even trained any standard recurrent neural network. And the reason for that is because training these networks is very unstable. Why is that? Because, well, in this time series domain, at least, the number of time steps that you can have can be very large. You might have, say, 100 or 1,000 time steps, right? And when you look at the gradient of the final state of this time series, it will need to sort of, like in this function, you are applying this u function again and again, right? Like you are multiplying your states with u again and again, which means that your initial h0 would have been multiplied by this u capital T times, where T is the length of the time series. Now imagine that if your time series is of length 100, and this u is slightly ill conditioned, that is, one of the eigenvalue of u is 2 and one of the eigenvalue of u is half, then your gradient will have a term similar to u to the power t minus 1, which means that one of the eigenvalue in your gradient would have blown to 2 to the power 99, and one of the eigenvalue would have vanished to 1 by 2 to the power 99. And that's precisely the reason why neural networks are, like these recurrent neural networks, are extremely hard to train. And people resorted to a variety of approaches, right? So for example, we had this approach of LSTMs or GRUs, which come up with much more complicated cells and gates to, in some sense, intuitively make the gradient of the function to be much more stable. Again, there is no formal guarantee here, and I think it's an open question how, like, why LSTM or GRU is sort of normalizing or like making these gradients much better or much smoother. But intuitively, like, I believe that that's what is happening, but they come at a cost, like, because these LSTMs or GRU cells will introduce more parameters. And in fact, for example, an LSTM can be almost 4 times more expensive than an RNN, and GRU is 3 times more expensive, both in terms of model size, also in terms of compute that you need, right? So we have designed this very simple method or simple block that we call FastRNN, which tries to sort of address this problem of instability of RNN almost head on, right? So the idea is the following, that, like, why was your RNN so unstable? Because whenever you see a new XT and like some, let's say, previous HT, your output HT plus 1 can be really, really different from your previous HT. So essentially, like, as you're going over this time series, your states can jump around significantly. And that's the reason why your gradients are exploding or imploding, right? So we said that we do not want our recurrent neural network to be this unstable. We'll add an explicit stability term. We will say that you will go to HT plus 1, sure, but and, like, you will follow this recurrent neural network update, but you are not going all the way there. You are going to go only up to, say, fraction alpha there, and then the remaining fraction beta will come from my existing state HT, right? Think of beta and alpha to be sort of like think of this to be a convex sum, that is, alpha plus beta is 1 and alpha and beta are both greater than 0. Again, we do not impose that, but, like, for intuition, you can think like that, right? So once you do such a thing, then what happens is that the gradient of this function now behaves something like this. That is, the eigenvalues of the gradient have terms like beta plus alpha into, say, some eigenvalue of u to the power t, and beta minus alpha times u to the power t, right? What does that mean? Like, think that, like, imagine that, your beta was 1 and alpha is 0. Then that means that all your eigenvalues are fixed at 1. So the system is super stable, but it is very bad also, because now you are sitting at h0 throughout. You are not updating your h0 at all, right? Because beta is 1 and alpha is 0, which means that ht plus 1 is equal to ht, which is equal to ht minus 1, and so on. So you are basically sitting at your initial state h0 throughout the neural network. You are not taking your input into account at all. So that's very bad. You can also model your standard recurrent neural network with it. You can set beta to be 0 and alpha to be 1. We know that that's very unstable. But now imagine that beta is around 1 minus 1 by t and alpha is 1 by t, right? So that is a very interesting regime, because now, even if you take t to be infinity, right? Like, forget t to be 100 or 1000. Even if you take t to be infinity, even in that case, your top eigenvalue will be bounded by a constant, and your smallest eigenvalue will also be lower bounded by a constant, right? Because I'm sure like, all of you would have studied in Math 101 that limit of 1 plus 1 by t to the power t goes to e or some constant. So yeah, I was saying that I really like this line of work because this is one example where actually TinyML exposed a problem, which then sort of made us think about standard ML, and probably like it enriched the literature for standard ML also, right? Because in standard ML, people said, if RNN is not training, let me add more parameters and make it more trainable, right? Which is seems like a fairly reasonable thing to do. But in TinyML, we have to think very carefully about why it is not training. Let me do something to fix RNN itself rather than just adding or throwing a bunch of parameters at it and hoping that it works out, right? So that's why like I really like this approach. I believe that like, when you think about TinyML, you are forcing your ML network or ML function to really capture the data well, and that can actually serve you well even in your standard machine learning regimes. Okay, so that like, philosophical point aside, let me sort of, talk about what this sort of FastRNN now means, right? So as I was saying that if you are setting your parameters properly, if you set your alpha to be about 1 by t, beta to be about 1 minus 1 by t, then we can show that this sort of recurrent neural network converges to a stationary point in a small number of iterations. It will have a bounded generalization error, which will be independent of t, right? And the reason for that is very simple. As I said, that if you have 1 plus 1 by t to the power t, that will always converge to a constant independent of t. So we are just using that sort of insight. But you can say that, oh, maybe in practice, that's a very sort of bad setting. Maybe alpha does not turn out to be 1 by t, beta does not turn out to be something like this. So luckily, that's not the case here. Like this is one situation where our experiments and theory was sort of matching very well. So so by that, what I mean is that we, on a bunch of these data sets, we like plotted, like we changed the number of steps and then we plotted the alpha value that we learned as part of this fast recurrent neural network. And we observed that naturally network was sort of, converging on a value which behaved almost as 1 by t, right? So here we are like on x-axis, we are plotting 1 by t. On y-axis, we are plotting what was the alpha that we learned. So a variety of these data sets we observe like that you indeed have alpha grow as 1 by t, right? Okay, so so FastRNN was very good. It could give us pretty good training, and in fact, it was already giving us accuracy which was very good. Like it was much better than accuracy of your standard RNNs, but it was somewhere close to accuracy of gated RNNs like LSTMs or GRUs, but it was not all the way there. It was like sometimes it was 3-4% worse. So we wanted to gain that that accuracy also. So for that, what we did was we introduced some gates in fast GRNN also. I will not go in details here, but the main idea is that rather than taking just a convex combination of the existing state and the previous state, we sort of take a gated convex combination of these various things. But the main point is that we are not going to introduce new parameters here. That is, our gates are also using the same parameters W and U. So they are sharing parameters, gates are sharing parameters, and based on that, we define this, this new formula. And after you do this, what we observe is that fast GRNN is indeed very similar in accuracy compared to gated RNNs. And now on top of this, you can apply some standard ideas like you can make both these matrices W and U to be sparse, you can make them to be low rank, you can make them to be quantized. And if you train them properly, like again, like if you throw in all of these together, try to train something off scratch, it doesn't work in most of the cases. But if you do this training properly, where first you introduce the low rankness, then you introduce the sparsity by hard thresholding, and then you introduce quantization, again by some version of hard thresholding, then what we observe is that we are indeed able to train a model which is fairly small. It's much smaller, like almost 20 to 80x smaller than your GRUs and LSTMs, but it is still almost as accurate. So here again, we are sort of, okay, I got some, anyway. Yeah, so here again, what we did was we compared our fast GRNN method against these standard methods like GRU and LSTM. What we observe is that in terms of accuracy on a bunch of data sets like, Google 12, Google 30, I'm sure you know about these data sets, which are around audio keyword detection, Yelp data set, which is a sentiment classification data set, DSA is a sort of sport activity recognition data set based on some IMU sensor data. And PixelMNest is like a standard digit classification data set. So on these, what we observe is FastRNN is again fairly accurate, very similar to GRE or LSTM. Sometimes it loses maybe 0.5%, 1%. Sometimes it's even slightly better. But when you look at the model size, compared to standard LSTM, we can be 20 to 80x smaller. Again, granted, some bit of accuracy is coming because of sparsity, but one important sort of aspect here is that compared to LSTM, our starting model itself is 4x smaller. So that's why we get that sort of impressive compression, and we're able to use it in various settings. Hi, Zana. You have a question? Great. So I think, yeah, we are almost out of time, right? So let me just conclude by sort of showing that, like, you can also sort of compare against a lot of these unitary architectures, which can be thought of as gradient clipping methods. And there, what we observe is that our method can be much more accurate than these methods, and still the amount of accuracy or like amount of RAM that we require is also smaller than these methods like spectral RNN, URNN, ORNN. There are a bunch of these methods. Okay, so that's all I had. So yeah, like if you have any questions, I'm happy to answer them.
Thank you, Prateek. This was awesome. It was exactly what we were hoping that you would be hitting on, like the key points. I think it's really, one question I have, just kind of pulling things together, right? So if you look at sort of where the field is going, how do you sort of see things evolving in the TinyML context? How should one be thinking about, let's say, 3 years down the road from where we are today?
Yeah, so that's a great question. So I've been sort of, thinking about it and struggling also to be true a little bit because things are evolving very fast, but the whole ecosystem is so divided and splintered that if you want to have a solution which is like really robust, really awesome, it becomes very challenging to have it, because in some sense then you will need expertise right from ML algorithms to quantization to deployment to the tiny chip that you are going to have. And that's where some of these new sort of frameworks that are coming up, like TensorFlow Lite Micro or framework by STM and like all those are, I think, great sort of directions where like it would be very sort of like, because they can sort of do a lot of chip specific optimization and making you sort of somewhat shielded from like understanding this end-to-end thing. But still there are going to be some challenges because like, not all the frameworks will be compatible with a lot of operators or new methods that you're going to come up with. As I said, that many times the methods that you're going to come up probably will be new. Like you are not going to be able to use existing blocks as it is and put them together, because that might be very expensive. So that's one thing that probably community should think about, that can we have a pool of TinyML operators, like the way we have ML operators, like, oh, we have LSTMs or we have our standard convolutions and max pool and this and that. Similarly, can we have a sort of community work around small operators that can be used to build really tiny models, right? So that's, I feel like, one direction which can be very fruitful. Another thing that I sort of see more and more is a lot of people are coming up with very interesting accelerators for these tiny devices, which are still very cheap from power point of view. So I know that ARM has some very interesting sort of accelerators called Ethos accelerator. There are a bunch of startups in this space. They also have some pretty interesting accelerators. So those can be a very sort of interesting sort of tools to exploit, because if you have accelerators, then that means that the amount of compute you can do can increase, like in some cases by almost a factor of 5 to 10, right? So your models can allow for a lot more compute, but because you are going to have to, like, have a very small form factor, and the memory will like if you have a lot of memory, then it will increase your power draw. So the RAM in many cases will still be constrained. RAM might still be constrained to 256 kilobyte or 512 kilobytes, which means that you might want to design methods which play better with RAM, but they can exploit these accelerators in a much better manner. And that means then also that, oh, if you are designing some method which is using sparse format, then how do you make sure that it is playing well with these accelerators? So a lot of these interesting questions come in, which tries to sort of look at both the algorithmic aspect as well as also tries to understand the platform on which these algorithms will be deployed on. And in terms of applications, I think vision is like definitely very, very ripe for a lot of these applications. In fact, we are very excited about this RNN pool work, which actually uses FastRNN, because it can now bring in fairly accurate, say, face recognition kind of things on M4 class devices. But in general, I feel vision is a field which is very hungry for very robust end-to-end solution. There are a bunch of uses for vision, and similarly, audio is another sort of domain where it has a bunch of uses. And finally, in domains like predictive maintenance, again, you can, like, I see a lot of usage for TinyML, and they are like very sort of interesting directions to look at.